Welcome to IMMYON. In the previous tutorial, we have seen what is meant by FEM and CIA. In this tutorial, we will be working on 1D problems. We are going to use Altair HyperWorks 13.0 version and always check that solver is selected as OptiStrut throughout our complete course. 1D meshing. For most of the linear static 1D analysis, we use the formula as MHPCLL. In the previous class, we have seen what is meant by MHPCLL. That is, M means material collector, H means hyperbeam, P means property collector, C means component collector, L means load collector, L means load step. When to use 1D elements? When one of the dimension is very large in comparison to other two, we use 1D elements. Element shape, line, additional data from user. The remaining two dimensions, the cross-sectional area. Element type, rod, bar, beam, pipe, axisymmetric shell. Practical applications are long shafts, beams, pin joint, connection elements. This is an example of 1D problem in which length is 5000 mm. Types of 1D element. There are different types of 1D elements. They are rod, bar, beam, pipe, axisymmetric shell, and these are the properties of the respected elements. So our first problem is rod element subjected to tensile force, in which one end is fixed and the other end is free. Length of the shaft is 500 mm, and which 1 lakh force is acting on x direction, and the cross section is circular cross section with dia 50 mm. This is the analytical solution, in which we get stress equal to 50.95 Newton per mm square and displacement equal to 0.12 mm in the analytical solution using the stress formula and displacement formula. Now we will be using the same dimensions and we will be working on the same problem in hyper mesh. Let's see what we get in software within less time. This is the HyperWorks panel. Okay, this is graphics area. This is material. I mean the chemistry CLL formula what we use, and these are located here. These are the snapshot and video recording options, and these are the new model, open model, save, and other tools. And these all are the tools which we use in our problems. This is model browser. This is entity editor. Now let's start with our problem. According to our formula, first we have to create material. So let's go to material first. This is the material collector panel. Click on it. Enter steel as material name. Color any color as you wish. Type isotropic. There are different types of types. Steel belongs to isotropic type. Select card image as mat 1. As we are going to do linear static analysis, the two on axial loads, we should select mat 1. Click on create by edit. Click on E new row. These are the properties of steel. And in this software HyperWorks, each and every letter E, G, new row, A, T, reference, G, ST, SC, SS. These all have default values. As if now, still default values are this only. There is no need to change them. So when we change or when we use a different material such as aluminum, copper, brass, anything, we should change the values according to the properties of it. Okay. Click on return. Again click on return to exit material panel. In the entities box you can see material title has been created. Right click on it. Expand all. Next we should create H hyperbeam according to our formula. 1D hyperbeam. Select standard section and here hyperbeam, and in standard section type select solid circle. As our cross section is solid circle, click on create. Here it is represented in radius. So we have problem with diameter of 50 mm. So radius is 25 mm. Enter 25 in it. Just click on somewhere and you can see it has been created. Circle has been created with radius of 25 mm or dia of 50 mm. So now we can see that the circle that created is out of the graphic area. To bring back in its position, click F on your keyboard. F is fit to screen. Anytime in HyperWorks, if the model goes out of the graphics area, just click F on your keyboard. That's it. Now click on model view to exit hyperbeam panel. Again click on return to exit panel. Now we have also created beam section. Now we should create property. To create property, click on property icon that is next to material only. Write property name. I am writing property steel. Name can be dependent on you. You can write any name you want. Select color. Type 1D. As we are doing the 1D problems right now, select type as 1D. Material as steel. Beam section as circle section. And here you can get one dot. How are they selected? Material and beam section. Okay, when you click on material, here you can see steel. That is the material you have created earlier in the starting process, that is shown here. So just click on it. In the same way, beam section. The beam section you have created earlier is shown here. Select that. That's it. Now click on create by edit. As if now there is no changes in this problem in the property panel. So click on return. Again click on return to exit property panel. Expand property, you can see property has been created. Now next step is component. Click on component icon. Give component name. Name can be anything. And color. Remember one thing here. The color you assign to the component is the color of your model you are doing. So select a nice color. No, check that there is no node card image has been selected. Click on property. Select the property you have created. Click on create by edit. Component has been created. Click on return. Now next is load collector according to our formula. But before going to load collector, first we should create two nodes and assign the rod. To create nodes, go to geometry panel, click on nodes. First enter 0 in x direction. Click on create. You can't see where the node has been created. Click F on your keyboard. You can see a node has been appeared. Now according to our problem, length is 500 mm in x direction. So write 500 in x direction. Click on create. Again click F on your keyboard to see it. So two nodes have been created with a distance of 500 mm in between them. Click return. Now we have to create rod. To create rod, go to 1D panel, click on rods. Select property as property underscore steel, that is you have selected. Select element type as C rod. Now click first node and click second node and automatically a rod has been created. Now click return. You can see a rod has been created now, but it is in one dimension and it is represented in 1D. So in order to view in 3D, click on this 1D traditional element representation. Change it to 1D traditional and element detailed element representation. You can now see in 3D representation. Now I'm going to say some controls using mouse. Press Ctrl on your keyboard and click left mouse key, which is used to control the model in your graphics area. Ctrl plus left mouse click. Now to move the model, Ctrl plus right mouse click. Now to zoom in or zoom out, Ctrl plus scroll down your mouse, I mean scroll button, use the scroll button to zoom in and zoom out. To zoom at a certain place, Ctrl plus click on middle mouse button, that is scroll button, and draw a line, a circle or anything. At a certain position you need to zoom. Okay. Now click F on your keyboard, that is fit to screen, and these are the isometric views option. Click Y X plane now, XY plane, that is default. Now In order to proceed with our problem, we should change this thing into 1D only. Click on 1D. Okay. Now rod has been created. So the next step is we should delete these nodes. In order to delete these nodes, there are two options. One is go to geometry panel, temporary nodes. Say clear all. Nodes have been deleted. Okay. There is another option also. There is a shortcut key in order to directly go into the temporary nodes panel, that is Shift plus F2. When you click Shift plus F2 on your keyboard, it directly goes into temporary nodes panel. In this, you can add and delete nodes. Click on clear all, click return. And according to our formula, MHPC has been created. So next is load collector. Click on load collector icon. Give name as SPC. SPC refers to single point constraint. Check that no card image has been selected. Click on create by edit. Click on return. Load collector has been created, SPC. Okay. Now we should fix this end. SPC refers to single point constraint as this end to be fixed. So to fix this end, go to analysis panel, click on constraints. Okay. Check all the degrees of freedom, d of 1, d of 2, d of 3, d of 4, d of 5, d of 6. You have already learned what is meant by degree of freedom in the tutorial 1. And check load type as SPC. Click on here, end, click create. You can see it is fixed now. Okay. And this size can be varied. Enter the size. 50 means 50. You can see size has been changed. I'm keeping this 20. That's my wish. And it depends upon your wish. Color can also be changed. Okay. Click return. Now we have to create load in X direction, right? Again go to load collector. Click force. Right force. And select a different color. Yeah, fine. And check that no card image is selected. Click on create by edit. Click return. And go to analysis panel only again. And click on forces. Enter magnitude. Magnitude equal to load that is going to act. Magnitude 1 lakh 5 zeros. So 1 lakh force has been written. And magnitude percentage is the size of the icon. So I'm keeping it 0.10 only. Load type as force. Direction X direction. As we are according to our formula, rod subjected to tensile force. So X direction. Click end. Click on create. Force has been created. Click return. The next step is load steps. In the same analysis panel, there is an option called load steps. Click on load steps. Give a name as load steps or anything. Select type as linear static. Now check the SPC box and select the SPC you have created. Same. Now check load box and select load force you have created. Click on create. Load steps have been created. In order to do complete analysis, you should follow each and every steps I mean MHPCLL to be done in order to do analysis. If you miss any of the steps, analysis won't be completed. Click return. Now we have created each and every steps, and our model has also been created. Now we need to do analysis, and we should find out the solution of, and see that are they exactly same as the analytical solution we have. So first, before doing analysis, we need to save this model. Click on File, Save as Model. Create a folder. Next folder, rod underscore tensile 1. Give a name that is understandable to yourself. Click on Save. After a successful save, you can see here model info. It has been saved. Now in the analysis panel, click on OptiStruct. Always check that export option is selected as all. Run options is analysis, memory default, and again click on OptiStruct. This is the HyperWorks Solver View panel, in which it solves the problem. If we have done each and everything correctly, then everything goes correct and we get a message as analysis completed. Now click on results. Which opens another panel. The panel has been opened. Okay. And this is our model. Now click on contour button. First we need to check displacement. Okay, here you can see displacement is there. Check on displacement. Click on apply. Yeah, we got the answer 1.213 e minus 01. Okay, this is the scientific answer. In order to view the exact fixed answer, click on edit legend option. Numeric format, to change the numeric format to fixed, click OK. 0.12. Okay, just remember the value 0.12 as displacement. And now stress, element stresses. As we have done axial load on it, see rod axial stress, check. Click on apply. 50.93 is this answer we have got. So same way, we got displacement as 0.12 mm in the analytical solution, and we got stress as 50.93 in software and 50.95 in analytical solution, but it is approximate value and this value is accurate and it can be taken. So we have successfully solved rod element subjected to tensile force. In order to save this, just close the panel. It asks save section as. Now let's go to another problem. In this problem, we are going to see bar element subjected to tensile force. In the previous problem, we have seen rod element subjected to tensile force. Okay, and in this the changes are, instead of rod we will be using bar, and instead of circular cross section we will be using rectangular cross section. Okay, these are the values. Rectangular cross section is 100 into 100, 500 and 1 lakh are the same. And please note down the solution of analytical thing. Displacement as 0.024, stress as 10 Newton per mm square. Let's go to our formula. Now I will be working on steps, on the same steps we have done for the rod problem only. Now I will be going somewhat speed or fast. First we have to create material. As there is no change in this material, I will be directly clicking on create by edit, giving the material properties e new row, click return, again click return, and next we have to create hyperbeam. Click on 1D, click hyperbeam, click standard section, and standard section type as solid rectangular. Click create and give the dimensions 100 into 100. Click on graphics area, click F on your keyboard and click on model view to return. Click return to exit hyperbeam panel. Next create property. Click on property. Write property name as steel underscore property. Color type 1D card image. Select P bar as card image as we are working on bar problem. Select material that we have created steel. Select beam section rectangular section. Click on create by edit. Click on return. Click on return. Okay, property has been created. Now let's create component. Click on component icon. Give component name as bar underscore component. I am giving it. It is depends on you. Give any name as you wish. No card image. Property as steel property. Okay, click on create by edit. Component has been created. Click on return. Now in the previous problem we have created geometry nodes. In the same way we should follow the same steps. Click on geometry, nodes, x0 create, and x500 create. Click F on your keyboard. Go to 1D panel. Now instead of clicking on rods, we should use bars panel as we are working on bars. Click on bars, select bar 2. Okay, select property as steel property, element type as C bar. Orientation is x-axis. Click on node. C bar has been created. Click return. Okay, to view in 3D view. Now it is a wireframe model. Just click on shaded elements. You can see it. Okay, this is the rectangular box we have with dimensions of 100 into 100. Go back to 1D. Click temporary nodes or shortcut keys shift plus F2. Click clear all. Return. Now we have to create load collector. Enter name as SPC. No card image. And click on create. Now again we can create another here itself. Name force, change the color, click on create by edit. Two load collectors have been selected. Now we need to assign the constraints and forces to it. So first we will be assigning constraint only. Go to analysis panel, constraints. But before directly assigning the constraints, first make SPC as a current component. Click on SPC, right click, make current. The reason is if you don't make SPC as a current component, the everything you are doing here will be going into force as force is current component. Click node, click create, return. Now in the same way, to create force, click force and make current. Click on forces analysis panel, forces. Magnitude is same 1 lakh magnitude and load types of force, and nothing is there to be changed. Just click on the end node, click create. Now the arrow has been changed. The reason is magnitude percentage is 100, so make it 0.10. It is common. Click return. Last step is load steps. Click load steps and everything is same, so just do one thing. Click on this, click SPC, click force, create. Load step has been created. Click return. Next step is save the model. Model has been saved. Click on OptiStruct. Check this all analysis memory default. Click again on OptiStruct. Progress is 0%. You can see the progress of the model. Job completed. Now now you can see we got a message as job completed, and we got another message, error 41. C bar 1 has an invalid orientation vector 0 or parallel to the element axis. I have wantedly done this problem to get this error because you need to know one error which is going to get. So this is the run summary. Go to up, come down. Okay, error 41. C bar 1 has invalid orientation vector 0 length or parallel to the element axis. So in order to solve this error, first you need to do is close the solver view. Okay, go to return and the message was invalid orientation, right? Go to 1D panel, go to bars, click on update elements all, change the orientation from x direction to y direction. Click on update, check all the boxes, click on update. Click return. Again go to analysis panel, click on OptiStruct, click on OptiStruct, click overwrite yes, wait for the solution. Analysis completed. So the reason was, as we are working on the problem that on bar, the orientation is on x direction, but in actual it should be perpendicular to the component. So the thing is, we have done this rod in the x direction, that is starting from x0 and ended at x 500, right? So the orientation should of the force should be perpendicular to it and should not be parallel to it. At first it was parallel to it, means x equal to x. Now it is perpendicular to x, that is y. So that's the reason. Now let's see our solution. Click on results. In future, if you get any sort of orientation problem error, check the orientation of the things. And it applies to only bar and beam problems, not for rod. Click on counter displacement, apply 2.38. We got the answer. 0.024 is the displacement. Now check analytical solution. Analytical solution is also same 0.024 as displacement. Now check the stress. Go to element stresses. Click on C bar by C beam axial stresses. Click apply. Stress 10. Stress 10. So analysis of bar element subjected to tensile force has been completed. Okay. In order to save it, just close the application. Save section, yes. Close the solver. Now just make it new. Click on new. Yeah, yes. Next. Next we are going to do beam problems. So before going to do beam problems, first we will see what is meant by concept of CDEF points. So in beam problems we need to enter some extra points named as CDEF. Okay. The meaning is, if you orient the hyperbeam's y-axis with the global y-axis and apply bending force in negative y-axis, then your C point will be in tension, showing positive stresses, and E point will be in compression, showing negative stresses, and points D and F will show zero stresses. And but if you orient hyperbeam's z-axis with global y-axis, then your D point will be in tension, showing positive stresses, and E point will be in compression, showing negative stresses, and point C and E will show zero stresses. Okay, to get this, we should work on the problem and write on this value C equal to y comma 0, D equal to 0 comma z, E equal to minus y comma 0, F equal to 0 comma minus z. And C, D, E, F points are this. I mean, they lie exactly on center. So let's go to our problem. Then you can understand what is meant by C, D, E, F. This is our problem. Beam element subject to bending force. Yeah, rectangular cross section, 500 mm length, 1 lakh newtons in bending force. Right? Stress is 300 Newton per mm square. Displacement is 2.38. Mm, let's do our problem. Go to Hyperworks, create material, all are same. Just click on create by edit. Click return. Go to 1D. Click on hyper beam, same. Click create. Enter 100 F. Click on model view. Click return. Click property. All are same except change the card image from P bar to P beam. Material steel, beam section, rectangular section. Click create by edit. Now don't close this box. I mean don't click return. We have seen CDEF points, right? Now we have to enter those CDF points in this box. I mean property box. Okay. Click on continuation line 2. Okay. Click C1, C2, D1, D2, E1, E2, F1, F2. Okay. Now, according to our problem, C equal to y comma 0, right? Total length is 100 mm. So 100 by 2, 50. So 50 comma 0, 0 comma 50, minus 50 comma 0, and 0 comma minus 50. We should enter the same values. 50, 0, 0 comma 50, minus 50 comma 0, and 0 comma minus 50. So we have entered the CDEF points. Remember one thing, CDF points should be given to beam problems. The problems we are working. Click on return. Click on return. MHPC has been created. Next is component. Click on component. Write anything, beam, no card image. Select property. Click on create by edit. Click return. Now create model. Click geometry, nodes. Next, we should create beam. There is no extra option to create beam, so beam is also created in bars only. Click on bars, click bar, select property as steel property, element type as C beam. C beam. As I already said, it should be perpendicular and orientation is y-axis, that is perpendicular to x-axis only. So it is correct. Select two nodes, click return. Once click on 1D, it has been created. Shift plus F2, clear all, return, load collector, SPC, create, force, change the color, create, click return, go to analysis, constraints, make SPC as current, create, click return, make force as current, go to forces. Now, according to our problem, load is 1 lakh newtons, acts on minus y direction, right? Bending force. So this is in x direction right now. Make it y. Enter minus before 1 lakh. Select the node. Click on create. It has been created. You can see it is now acting in minus y direction, so that bending force is seen. Click on return. Click on load steps. Select the node SPC force. Click create. Click return. File. Save as model. Beam underscore bending. It has been saved. Click on OptiStruct. All analysis memory default. OptiStruct. Analysis completed. Click on results to view results. Click on contour. Click on displacement. Apply. Edit legend. Scientific to fixed. Okay. 2.44. Let's check our problem. We got displacement as 2.38. Now let's check stresses on CD of points. Now C bar by C axial stresses, if we click on this, it shows us 0 because this is beam problem, and we have also given CD of points. We should check at each and every point. C bar by C beam long stress SAC. Apply. 300. We got stress as 300 in C direction. Stress equal to 300. Okay, answer is correct. Now let's check it with other. Stress at D point. Apply 0. Okay. Stress at E point. Apply minus 300. Stress at F point. Apply 0. Okay. C 300 and E 300. Go to our theory. Here you can see hyperbens y-axis with global y-axis and apply bending force in negative y direction. Then your point C will be in tension showing positive stresses, and E point will be in compression showing negative stresses, and D and F will show 0 stresses. Okay, this is the point we have got right now in our problem. Okay, in the same problem, if you orient hyperbeams z-axis with global y-axis, then your D point will be in tension showing positive stresses, and E point will be in compression showing negative stresses. Now we will be seeing this by orienting the same problem with z-axis. Close this. Return. Go to 1D panel. Go to bars. Change the orientation from y-axis to z-axis. Select elements all. Property as steel property. Element type as C beam. Click update. Check all. Click update. Click return. Click analysis again. Click OptiStruct. All analysis of OptiStruct S. Analysis completed. Click on results. Click on counter. Check the stresses. Now first check C. It is 0. D 300. We got the answer now, as you can see. Right? And F 300. Close. Save section. Yes. Close. This is what CD of points are. Okay everyone, we have seen how to work on rod, bar and beam problems. If you need models for all of this, please go and sign up in our website, that is www